and welcome to this tutorial on scientific notation and also significant figures. Now, this is often seen as a very dry topic, sort of like a fiddly thing you have to do to write numbers that satisfies certain people. But actually underlying this topic is a tremendous amount of power to understand the world. And I won't have time in this tutorial to really show that to you, but I'm planning a tutorial in the near future which will be called Powers of 10. And from my science background in physics and biology, I'll be talking about the amazing breadth of phenomena that you can describe once you can master powers of 10. And the way that we in science sort of utilize powers of 10 is with this tool called scientific notation that I'll describe for you here. So this really stems from some understanding of indices that we covered in a recent tutorial. So let's basically think about some numbers that we're quite familiar with. So for example, we're very familiar with the number 1000, and we can think of 1000 as 10 times 10 times 10. And thinking about the indices, thinking of 10 as a base, we are very comfortable that we can write this as 10 to the power of 3. Once you've understood this and using some of the rules of indices, you'll be completely fine with scientific notation. Let's think of a larger number. Let's think of 1,000,000, and I'm going to use this slightly old-fashioned way of writing numbers where I separate each group of 3 zeros because the numbers become quite unmanageable. Now, 1,000,000 is 10 multiplied by itself 6 times. You can also think of 1,000,000 as 1,000 squared, either way. But for our purposes, though, we can think of it as 10 to the power of 6. So when you start to think in terms of scientific notation, you want to start to have a very easy translation between words like 1,000,000, which stands for this number, and immediately think, oh, that's just 10 to the power of 6. Using our rules of indices, we can immediately see that 10 to the power of 6 is 10 to the power of 3 times 10 to the power of 3. So it's obvious that 1,000,000 is 1,000 times 1,000. I'll just do one more of these sort of big numbers. Let's think about 1,000,000,000,000, which is 1,000,000 squared. And you can see why we have scientific notation, because it's very tedious writing down all these zeros. So this is 1,000,000,000,000. It's 10 multiplied by itself 12 times. I'm not going to write all those tens, but in saying that it's 1,000,000 times 1,000,000, I can very easily write this, and then of course we see that 1,000,000,000,000 is 10 to the 12. Now you might say, well, we don't really need these very large numbers, and that was true probably up until the 1700s. Once there was a scientific study of astronomy which was quantitative. People could start to actually put numbers to things like the size of the Earth, the size of the solar system. People started to have an inkling about the size of the universe. And so the reason that you have to have a notation for numbers like 1,000,000,000,000 and so on in science is because, as science has progressed, we have discovered very large things and also very small things. So the largest thing that we know of is the observable universe, and that has a size of let's see if I can say it in words. It would be something like 100 million meters. We would never say it like that. What we would say is that roughly it has a size of 10 to the 26 meters. And you see how useful this scientific notation is. To use a power of 10, we can indicate the size just by a number that we can all understand. 26 is a number that we can understand. We can say the volume, and this is really neat now because I don't think you would be able to say the volume of the universe in cubic meters in words. It would just be too cumbersome. But we can easily do this. The volume would be approximately 10 to the 26 all cubed, because roughly speaking, a volume of something is the cube of its linear dimension if it has a roughly symmetrical shape. And using our rules of indices, we know how to do this. When we have a power, all raised to a power, we just multiply these. So the volume of the universe then, let's see, 3 times 26 is 78. So the volume of the universe would be 10 to the 78 cubic meters. What about something very small? Well, an atom is quite a small thing. An atom is 1/10,000 millionth of a meter. And again, we don't use that language. We would say an atom is 10 to the minus 10 meters. Remember that when we have a negative index from the tutorial on indices, what we mean is 1 over that base to this index with a different sign. So 10 to the negative 10 means 1 over 10 to the 10. So it's 1 10 to the 10th of a meter, and 10 to the 10 is 10 times 1,000 times a million, 10,000 million. I think the smallest thing that we've actually measured is a quark, which is a constituent of a nucleon, and the size of a quark is 10 to the minus 17 meters. So you can see these powers of 10 suddenly give you the ability to have a common language to describe the smallest things that we know, the largest things that we know, to work out volumes of things. The volume of a quark then would be 10 to the minus 17 meters all cubed, which would be roughly, and again, power of a power, we multiply the indices, that would be 10 to the minus 51. And so you could even do something insane. You could say, what's the volume of the universe compared to the volume of a quark? Well, that's 10 to the 78 compared to 10 to the negative 51. So it is 78 plus 51 times bigger, so that would be 129 would be the relative, is that right? 10 to the 129 to 1. I mean, obviously a bit silly at this point, but you get the idea how useful this is. Now this is really just powers of 10. When we speak of scientific notation, there's another bit if we want to be more precise. That is to put a number in front of this. So let me use an example, which is the speed of light. Speed of light is, I've got it here on my calculator, I can show it to you. It's 299799248. It's that number of meters per second, and that's a whole other amazing sort of tutorial maybe in the future to talk about how extraordinarily large the speed of light is. But let's not go on that detour right now. Let's just think about this number. This is not a useful number, okay, to think about. There's too much information there. There's 1, 2, 3, 4, 5. There's 9 digits there. So, roughly speaking, this is 3.0 times 10 to the 8 meters per second. I just make sure I've got that right, yes, because this is thousands, millions, it's hundreds of millions in size. So 10 to the 8 is the approximate size of the speed of light in meters a second. And then from this exact value, we can write down this prefactor. And in scientific notation, we always write the prefactor of 10 to a power as a number and then a decimal point and then other numbers after that according to the precision that we want. Now this is quite imprecise. If we wanted to be more accurate, we could write this as, for example, 2.99, and let's say I wanted to write that digit. I wouldn't write 7 because you see the next digit is 9, so this pair is much closer to 80 than it is to 70, and so to indicate that I would write an 8 here rather than a 7, and then times 10 to the 8 meters per second. And here I've used 1, 2, 3 decimal places, or alternatively you could say I've written 1, 2, 3, 4 significant figures. Here I've used 1 decimal place, I've used 2 significant figures there. The rule of significant figures is that the last figure you write, you either use the digit you have if the one following is 4 or less, or you make it 1 higher if the following digit is 5 or greater. So if I just make up a number, let's make up a number here, 7, 2, 5, 1, 4, so 72,514, I can write this to one significant figure, would just be 7. I ignore all the other digits. I have to indicate the size of the number, and so I would write all zeros, and that would be one significant figure. Writing it to 2 significant figures, I would write 7, and then I would not write a 2 here because the next number is 5. And so the rule is if the next number is 5 or greater, we round up the preceding number. So to 2 significant figures, this would be 73,000. Okay, so that's 2 significant figures. And if I were to write it to 3 significant figures, I would write 72500. That's 3 significant figures. Let me just do one more example. Let's have a small number now. Let's imagine I have 0.00284. Then to one significant figure, I would write this as 0.00 to indicate the size. And then this number here, because the next number is 5 or greater, would be 3. So that's that number to one significant figure. If I'm writing this number to 2 significant figures, I would write it as 0.0028. That's 2 significant figures. If I wanted to write this number in scientific notation, I would bring this 2 all the way in front of the decimal place. So I'd have 2.84, and then I have to indicate the size using times 10 to a power, and this number is roughly as 1,000th, and so this would be 10 to the minus 3. That's the exact number in scientific notation. This exponent here essentially tells you how many places you have to move this number to get it to the decimal place, and here it was 1, 2, 3 places I had to move it. Alternatively, this number here in scientific notation would be 7.2514. You see, I've taken the 7 now this way to the decimal place, and then times 10 to the power of 4, because the number is roughly 70,000. You can always do this kind of sense check. The number's roughly 70,000, and 10 to the 4 is 10,000, so I have 7 lots of 10,000. So I hope this has been helpful and also interesting in thinking about scientific notation. The utility is not in this kind of pernickety writing numbers, it's really in being able to manipulate very large or very small numbers to describe the amazing universe in which we live. But also it's important to know how to be able to manipulate numbers here in terms of converting numbers to scientific notation, and also in terms of using a sane number of digits. This number for the speed of light is not helpful. It has too much information for most purposes. We want simpler ways to represent it, and for that we need to know the procedure for significant figures. Right, I hope that was helpful, and I'll see you next time.